Hello, my name is Eduardo, and in this video we are introducing our paper Real-Time Locomotion on Soft Grounds with Dynamic Footprints. When virtual characters move on loose grounds like sand or snow, the ground should deform under our feet and in return affect our motion. Following our last work, we developed a multi-layer approach to model such two-way interactions in real time by using an efficient and yet versatile controlling method. This technique could allow to adapt the gait of virtual moving characters in real time based on the irregularity of the terrain and the possible displacement in the ground that it might occur. In this paper, we introduce a physically based model for computing interactions with the ground in real time, from only the kinematic motion of the virtual character. This method considers elements such as the balance of the character, the feet speed, or the nature of the terrain. Along with a standard strain-stress relationship, we compute the dynamic deformation of the soil for a given pressure applied by the character. The resulting footprints lead to a visual improvement in outdoor scenarios, while the procedural deformation results in a consistent change in the character's motion, ideal options for enhancing the visual realism in video games and virtual reality applications. The area of contact is computed efficiently as the character moves on the ground. We use recasting on a local window of the terrain set to estimate the total area where the foot collides, represented by the blue rays. In addition, we also define an area around the foot, displayed in yellow, to define where a possible vertical displacement might occur due to the impact. Our model estimates automatically the forces that the character applies to the ground, based on its kinematics and the nature of the terrain, such as the weight and the balance in blue, the forces generated by the change of momentum that occurs in the feet when they hit the ground, in red, or the resulting ground reaction forces, in green, with equal magnitude but opposite direction as the forces that the feet exerts into the terrain. This force model can be used for other kinematic inputs, such as running or other arbitrary animations. For a real-time deformation, we introduce a plastic model for terrain compression. Such model takes the previously calculated time-varying force that the character exerts in the ground and estimates a pressure using a linear stress-strain relationship, defined by the terrain characterization, which is based on parameters such as the Young modulus or the Poisson's ratio. Both force model and terrain deformation can be used to characterize multiple types of terrains. Besides, we use an inverse kinematics layer to adapt the pose of the character to the deformation, changing the motion of its legs or overall height depending on the impact to the ground. For the experiments, we have modeled 4 scenarios corresponding to the materials previously shown. The calculation of forces and ground deformation does not affect the height performance of such lightweight methods, which remains highly efficient even for real-time applications and to be applied in game engines like Unity. This could allow the method to be implemented not only in video game applications but also in virtual reality scenes to improve the coupling between real humans and the impact that they may have based on the interaction with the environment. This method is applicable to different characters, which change the deformation of the terrain accordingly based on their morphology and the nature of the motion. While increasing the weight could lead to deeper footprints, a bigger size of the feet could help to distribute the weight over a larger area, causing shallower deformations. Also, as we described previously, the type of motion and speed of the feet directly affect the corresponding deformation. If we compare the approach for terrain deformation, in the previous method the results remain unchanged with respect to the dynamics and morphology of the character, as well as having a parameterization based more on the appearance than on the desired physical response. In the current method, the deformation is reproduced continuously, and not only takes into account the geometry of the character's feet, but also automatically adapts to their speed, the character's mass, and its morphology. In addition, our method also works with other types of input animations, for example, motion capture data, or even fully physically based characters, opening the door to other areas of research where interactions between the character and the environment are an essential element in generating the animation. We hope you enjoy it. Thank you!